everybody, good afternoon, or, well, good morning, good evening. I don't know what time it is when you're watching this video where you're at. Whatever time it is, it's always a party in the Calculus Fun Room. So welcome back. In this video, I want to talk to you about the product rule and quotient rule, the shortcut rules, if you will, for derivatives. So in the prior video we had began talking about some derivative rules, and one of the rules we talked about was the derivative of a constant was 0. We talked about the derivative of really any linear function was the coefficient, right, its slope. We talked about the power rule. So we said we had x to a power, right? We would bring the power down, take one away, and we said this was true for any value n, right? N can be any real number. And we also talked about the derivative of the base e exponential being itself. And then we talked about the sum or difference rule. So I'm going to get lazy and use the prime notation. So if we have f plus g that we're taking the derivative of, we can take the derivative of each individual function. So I thought about the operator moving over the plus or minus sign. We called this the sum or difference rule. So in this video we'll continue to see these rules, and then we'll introduce the product rule and the quotient rule, and we'll look at some specific examples how to apply those rules. So first let's take a look at the product rule. So what I'm going to do here is write out what the product rule says, and let's use the Leibniz notation and the prime notation. So probably the easiest way to write all of these, right, is with the prime notation. So let's say we're looking at f times g and we're taking the derivative of that. So I have like the first function times the second. I would have derivative of the first times the second plus first times derivative of the second. So in essence, we kind of alternate taking the derivatives of each of these products and we add that together. This would be what we call the product rule, right? And if we write this in Leibniz notation, right, we would have the derivative of f of x times g of x. So that would be, say, the derivative of the first function and then times the second and then plus the first times the derivative of the second. Something else to keep in mind, the order in which you do these derivatives doesn't matter, right? Addition is commutative. So, 4 plus 3 is the same thing as 3 plus 4. So the order in which we do these doesn't really matter. Okay, so again, like I prefer to do in most scenarios in my videos, I don't want these videos to be overly lengthy. So I'm not going to provide a proof or derivation of the product rule. All calculus textbooks will provide those rigorous mathematical proofs for you. Definitely you should read those. You should take a look on the web. I'm sure you will find a proof of the product rule if you search for it. Just for the sake of time, right, let's move forward and talk about how we would apply this rule, because that is ultimately how most of us are going to deal with derivatives in a calculus course. So let me just go ahead and start a new page. So let's suppose that I have the function, let's say we have f of x equals x squared times e to the x, and we want to find f prime. So if I follow my product rule, right, keep in mind finding f prime is that I'm going to take the derivative of this product, x squared e to the x. And again, I'm going to get a little lazy and use the prime notation here. In the next example, I'll use the Leibniz notation. So the product rule says, like, if I have a first function times a second function, I'm going to do derivative of the first and then times the second plus the first function times the derivative of the second. So then I'll come back and I'll complete each of those derivatives. So the derivative of x squared, using the power rule, we would know is 2x, and then we just multiply by the second function. Then we just recopy the first function, and then the derivative of e to the x is just e to the x. And so technically we are finished with our product rule for this particular example. Some things you might see some textbooks do, or solutions manuals, or even some websites. Right? There's some websites out there where you can tell the website to take a derivative, and it will symbolically tell you the derivative. Sometimes the answers are given in this form. Sometimes they'll do some factoring. So we have an x and an e to the x in common with both of those. So if we factor that out, we're left with 2 plus x. So either one of those would be an acceptable form of the derivative using the product rule there. All right, let's take a look at another example. In this example, let's say we want to, let's find the equation of the tangent line to, let's say, h of t equals, I'm just going to make up some numbers here, 3t minus 5, and let's say square root of t plus 1 over t. And we want to find that equation of the tangent at t equals 1. So again, in prior videos, we've talked about the equation of a tangent line. The slope of that tangent line comes from the derivative of the function, right? So procedurally here, right, what we're looking for is we want to find the equation of the tangent line, something like this, right? And the slope comes from the derivative, right? Slope is the derivative at t equals 1, right? So I'm using x's and y's in this equation of the tangent line, although the y's we have here are h's, the x's we have here are t's. I'll come back and fix that in a minute. So we need to find the derivative, right? We need h prime at t. So h prime at t is going to involve a product rule. Right? So I'm going to do, here's my first function, here's my second function. So I'm going to do the derivative of the first, let me just write that symbolically, times the second plus the first times the derivative of the second. And actually, let me stop for a moment here, right, and just point out that in the prior video, when we didn't know the product rule, had we been given this function to take the derivative of, what we would have had to do is like FOIL all of this out. And we would have to multiply all of these terms together to give ourselves basically one big polynomial-esque looking equation. Right? We would have to get rid of the product of these two binomials. Now in this case, we're going to skip that work, and we're going to approach this as a product rule. Right? And then, so I noticed I have a typo down here. So here's derivative of the first times the second plus first times derivative of the second. So let's apply that product rule. So a couple things we'll remind ourselves of here is that when we differentiate a square root, and keep in mind we're looking at that as t to the 1/2, right? And when we differentiate 1 over t, we're looking at that as t to the -1. So when I do those derivatives, I'm going to remind myself of those power rules that I would use there. So the derivative of 3t minus 5, the derivative of 3t is just 3. The derivative of -5 is 0. So I end up with 3 times root t plus 1 over t. And then plus, so then I have 3t minus 5. And I'm going to differentiate this function. So I'm going to differentiate root t, that's 1/2 t to the 1/2 minus 1 is my power rule. And then when I differentiate this guy, I'm going to bring the negative in front, and then I'm going to have -1 minus 1, which is -2. So a little bit of simplification there. I have 3 times root t plus 1 over t, and then plus, got 3t minus 5, and then this is really in the denominator as a 1/2 exponent, which is a square root, and then this is really in the denominator as a positive exponent. So here's my derivative. Now I'm not going to go crazy simplifying this algebraically because I'm about to plug in t equals 1, right? So I want this equation of the tangent line at t equals 1. So I'm going to come down here then and plug in t equals 1 into my derivative, right? So the slope of my line then is the derivative evaluated at t equals 1. So we can see when I do that, I'm going to get square root of 1, which is 1. I'm going to get plus 1 over 1, which is 1. Right? So I'm getting 3 times 2, basically. And then 3 times 1 is 3. And then when I plug 1 in here, I'm going to get 1/2. When I plug 1 in here, I'm just going to get 1. So what I really end up with in this case, this is what? 3 times 2, which is 6. 3 minus 5 is negative 2. I have 1/2 minus 1, that's negative 1/2. So I have negative 2 times negative 1/2. So this is really what? Positive 1. So I get 6 plus 1, which is 7. So the slope of my tangent is 7. Now, to find the equation of my tangent line, right, again, we're going to use, I prefer to use the point slope formula. Right, so I'm going to come back to green here, and I'm thinking of like y minus y1 equals m times x minus x1. So we know the slope is 7. We know the x value, the t value is 1. Right? So let me just rewrite this, in the language of the variables that we have here. So again, we know the slope is 7. I don't know the y value at the moment. I know the x value was 1. The t value was 1. So what's our h value? Right? So I need to just come back to my original equation, plug in t equals 1. So where is that at? Let me scroll up for a moment. Okay, so here's my original equation. So I want the y value on this equation. So I'm going to plug t equals 1 into that equation. So if I plug t equals 1 into this equation, I'm going to get 3 minus 5, which is negative 2. I'm going to get 1 plus 1, which is 2, which gives us negative 4. So let me come back down here, and let's note that h of 1, I'm going to put this in red, right? H at 1 would be negative 4. Right? So we're going to have the negative 4 here. So if I solve for the h value, right, we're going to have what? 7t. I'm going to have minus 7. This is really plus 4. So I'm going to subtract the 4 over. I'm going to have negative 7 minus 4. So my tangent line is really 7t minus 11. So here's the equation of my tangent line. Now, we discussed this briefly in the prior video, and I want to go ahead and remind ourselves of one way to check our work here. So what I should do, right, visually, I can graph the original function, and I can graph my tangent line, and I can see that those, are correct, that my tangent line is correct. If it's not correct, then I know I have a mistake somewhere and I need to come back and check. So I'm going to pull up Desmos.com real quick. Let me pause the video so you don't have to watch me type all of this in. Okay, so I brought up Desmos.com and I plugged in my original function, and we can see that is being graphed here. And what I like to do in Desmos is use function notation, so I called that f of x. Right? And then I'm going to just point out to myself that if I plug 1 in, I get a y of negative 4. So we're checking that point that we found on the graph. Right? All right, now what I'm going to do then is graph my tangent line. So let me scroll back down. My tangent line was 7t minus 11. So let me bring Desmos back up, and let me delete that. So I'm going to do h of x equals 7x minus 11. And we can see it looks like we're tangent to the graph, and it's at t equals 1, right, where we're supposed to be tangent. In fact, let me plot that point. Let me do 1 comma f at 1. So it's going to plot that point for me. Let's label it. That'll be fun. So there's the point of tangency. It looks like we have a tangent line, like we've done correct work. Let me scroll and zoom out a little bit here, and you can see the tangent line in red appears to be glancing below to the function there, right? So it looks like we have a good equation for our tangent. Now keep in mind, if I'm using other technology like a Texas Instruments graphing calculator of some sort, I could take the same approach, hit the y equals key, type in my original function in y1, type in my equation of my tangent in y2, and then I should be able to graph and see the tangent come in to the function. So it looks like we're good at the point 1, -4. We have the tangent to the graph there. All right, let's come back to that homework problem, and let's look at finding the equation of a normal line. So one of the homework questions you might have in a section like this would ask you to find the equation of a normal line. One purpose of doing this might be in a physics class, and let's suppose we had a table, and on this table we had, let's say, we had a book or something like that, right? So we know gravity pulls down on the book, and in order for the book to stay where it's at and not, fall through the table is exerting what's called a normal force. So this might be gravity, this might be the normal force, and therefore the book stays there. Now in a physics class you'll learn about this a little bit deeper. Also in a Calc 3 class you'll learn about normal forces in relation to motion along a curve. You might see motion along a curve. Like think about riding a roller coaster. If I'm on my roller coaster, the tangent represents the idea of like where I'm heading. So like for example, suppose the roller coaster flies off the track all of a sudden. Let's hope that never happens. I'm going to move along the tangent. So that shows me my velocity, my direction of where I'm heading and the speed. And then we have a normal force as well. So one of the homework questions in the section says find the equation of the normal line. Now this, once we have done the derivative and we have found the slope of the tangent, this is pretty straightforward. And if we look at this graph that we have here, let's suppose our slope, and I have that tangent decreasing, right? But we know our slope is +7, so let's say my curve looks something like that, right? And my slope is 7, then the slope of the line that's normal, that's defined as the line perpendicular to the tangent. So for the normal line, the slope of the normal line is the slope that is perpendicular to the tangent line. And we know that two lines are perpendicular when their slopes are negative reciprocals of each other. So if we have a problem asking us to find the equation of a normal line, we're basically going to find the slope of the tangent and then take its negative reciprocal. And then in this case, we would have y minus -4 equals the slope of our normal line and x minus 1. All right, and then just to visualize this, I brought my Desmos graph back up, and here's the equation of my normal line after I solve for y. And let me turn off the tangent, and we can see here's our curve, and then here's our line that is perpendicular, that is our normal line. So that's a nice way to visualize that we have the correct equation there. All right, and I want to point out something else really cool to you in regards to the TI as well. So for example, let's suppose on this problem, let me come back to the problem. Let's suppose I want to just check my derivative. So I have my original function that we were given up here. Let me zoom out a second. So we have my original equation that I was given up here at the top, and then I have my derivative down here. I had a simplified version a little lower, right? So here's my derivative, which I simplified as much as I wanted to. I didn't want to have to FOIL all of this out, gather like terms, so here was my simplified form of my derivative. So let's suppose that I just want to check that derivative. And I want to do this on my calculator, right? So what I'll do on my TI is here's my original function. Here's the tangent. Let me delete that. Right? So I want to check my version of the derivative to the calculator's version of the derivative. So I'm going to type my version of the derivative into y2 here. All right, so pause the video again real quick, right? Here's the version of the derivative that I'm plugging in, right? What we simplified. And here's me typing that into y2. And so, I just want to point out to you when you type in fractions. So notice in this first fraction here, the numerator is a monomial, the denominator is a mono. That's one term in that monomial. But when I type a fraction in and I have more than two terms in a numerator or denominator, what I want to do is parenthesize those. And I even made the mistake here. So 1 over 2 root x was in the second piece of our derivative. And I want the denominator in parentheses, right? I want 2 root x in its own parentheses. Okay? So I actually left the parenthesis off here. So I'm going to come back and insert the parenthesis. So I'm going to do second delete is an insert key and put the parenthesis there. So I'm encasing the whole thing in parentheses in that denominator. And again, this denominator has x squared, which is really just one term, right? It has t squared. So I'm just not going to encase that in parentheses. It's not necessary. Now what I'm going to do is have the calculator find the derivative of the first equation. I'm going to hit math. And I'm going to choose number 8, the numerical derivative. So again, I'm taking the derivative with respect to the variable x, and I can type the whole equation in here. Or what I can do is tell the calculator to take the derivative of y1. So I don't want to have to retype all of this in y1. So what I'm going to do is hit the vars key, which stands for variables. What I'm looking for is a y variable. It was a function, and it was equation y1. So it is going to take the derivative of that equation in y1. And then I want to evaluate the derivative. Now, what we just did a second ago was we plugged in x equals 1, and it gave me the number 7. But what I want it to do is find the derivative for every possible value of x and plot that graph. So I'm going to plug in x, right? I'm going to have it find the derivative for every value of x. Now, what I want to do, here's y3 is the calculator's version of the derivative. y2 is my version of the derivative. I don't really want to look at y1, so I'm going to hit enter on the equal sign and just turn it off. Now I'm going to go to the table. I'm going to do second graph and go to the table. And I can see that my derivative in y2, calculator's derivative in y3 match numerically. So for each value of x, for x equals 7, I can see these two match. So my derivative and the calculator's derivative are equal to each other. So that's kind of a cool way to be able to check my derivative using a TI calculator. Now, of course, I always could hit graph and see that the two graphs are the same. So there's my version of the derivative, and then we can see lying right on top of that is the calculator's version of the derivative. Now, usually I don't graph because sometimes the graphing can take really long, whereas filling in the table can be quicker. Alright, so I pause the video again. I'm bringing up Desmos. I'm going to take really kind of the same approach that I did in the TI. Right? Let me bring up the TI real quick. So in the TI, I had, y1 is my first equation. I had my derivative as the second equation, and then I had the third equation, the calculator's version of the derivative. So I'm going to take kind of the same approach here. I have, let's say the first equation is the original function, and I don't really want to graph it, so I'm going to click here to turn it off. And then here's my version of the derivative, and then I want Desmos's version of the original function's derivative. And this is really simple because all I'm going to do is use prime notation. I'm going to do F and hit apostrophe on my keyboard. And then there's its version of the derivative. It is calculating the derivative for me. That's really cool. All right, so we could see that if I turn that off, my derivative's in blue, and when I turn that on, the Desmos derivative is in black and lies right on top of it, and we can see that they're equivalent to each other. Okay, so now let's take a look at the second and last rule that we're going to discuss in this video, which is the quotient rule. Okay. So the quotient rule deals with exactly what you would expect it to deal with. This is the quotient. So we would in essence be looking at f of x divided by g of x, and that we are taking the derivative of. Right? So the quotient rule basically says this. I'm going to do bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. So there's my, shortcut, my efficient prime notation. And then we could use the Leibniz notation as well. So we could have the derivative of a top and a bottom. That's just how I like to say it. Helps me remember it. Right? So I'm going to do, let me write in Leibniz form here. So I'm going to do g of x and then times the derivative of f of x. I'm going to do minus the top, f of x, times the derivative of the bottom, all over the bottom squared. There's a kind of neat way to remember this as a mnemonic. Right? I'm saying it in words. That always helped me remember it. I had one of my students show me this, which I thought this was kind of cool. So there's high, the top function, and there's ho, the low function. So what I would do in that case, I'd say bottom times the derivative of the top. I'd say ho d high. So d high means derivative of the top. So I got ho d high and then minus high d ho. So that means derivative of the bottom all over the bottom squared. Which is kind of a neat little mnemonic to remember that. Ho d high minus high d ho all over ho squared. So that's the quotient rule, right? Again, you want take a look in a textbook, calculus textbook, take a look online if you want to look for the proof of the quotient rule. Probably would take us about 10 minutes or so to do that proof. I don't want to take the time to do that proof. I want to stay focused on applications. So let's go ahead then and jump to an example here. Okay, so in this example, let's suppose we have the function. I want to continue to try using, different letters here. So let's say I want to take the derivative with respect to theta. That is supposed to be a theta. Let's say I have theta squared minus 2 theta plus 1 all over, let's say we have 3 theta plus 5. All right? So here's this rational function, right? This quotient, and I want to take the derivative of that expression. Right? So again, my independent variable here is thetas, and I'm taking the derivative with respect to that independent variable. So again, I'm going to get a little bit lazy in how I write this, and I think I'm going to run out of room in my digital paper. So let me come down here. So I got ho d high. So I got ho, the bottom, d high. So I'm going to take the derivative of the top, right? Ho d high, right? Minus, and then top, times derivative of the bottom. Right? So again, ho d high minus high d ho all over ho squared, the denominator squared. And then I just need to simplify that, right? So I have the top, which was 3 theta plus 5 here, and then 2 theta minus 2 would be the derivative of the second term here in my numerator. So I have theta squared minus 2 theta plus 1. Derivative of theta squared is 2 theta. Derivative of negative 2 theta is negative 2. The derivative of 1 is 0. And then I have theta squared minus 2 theta plus 1, and then the derivative of 3 theta plus 5 would be just 3, and then I have all of this over 3 theta plus 5 squared. Now, honestly, we're done with the derivative at this point. We don't have any more derivatives to calculate. When you do this problem in most textbooks, right, they're going to clean this up a little bit. Now, I'll tell you that in the denominator, what you will usually see in a solutions manual is they do not multiply out that denominator. And there's a reason for that we'll see very soon, right? But we typically want to leave things in the denominator in a form that's factored. Now, I'll go ahead and mention one of the reasons here. I might be looking for where my derivative is undefined. And my derivative would be undefined where I have division by 0. It's going to be a lot easier to identify where the denominator has division by 0 in a factored form. If I FOIL all that stuff out, then I got to solve a quadratic, like theta squared minus 2 theta plus 1, right? So if I FOIL all this out, I have a quadratic like this, and then I got to either factor again or use the quadratic formula. So we're going to leave the denominator in a factored form. But what you'll see a lot of times is they'll multiply all of the stuff out up here to just clean up the expression and gather like terms. So in this case, I'd have 3 theta times 2 theta, which would be 6 theta squared. And then I'd have 3 theta times negative 2, which would be negative 6 theta. And then it had 5 times 2, which would be 10 theta. And then it had 5 times negative 2, which would be negative 10. So there's those first two being multiplied. And then if I distribute here, I would have 3 theta squared, and then minus 6 theta plus 3. And then all over the denominator squared. Again, I'm not touching the denominator. I'm going to leave it in a factored form. And then if I clean this up, right, remember technically I need to take the subtraction sign and distribute it to every term. So I'm just going to do that verbally. So I'm going to have a minus 3 theta squared. So I got 6 theta squared minus 3 theta squared is positive 3 theta squared. And then I have, well, let me go ahead and combine these, right? This is really 4 theta, and then minus a minus is plus 6 theta. So 4 theta plus 6 theta is 10 theta. And then I have negative 10, and then this is minus 3. So negative 10 minus 3 is negative 13. So there would be my most simplified version of this problem, this expression, where we used the quotient rule. All right, let's take a look at another problem here, similar to something you might see in a homework set. And the purpose of this homework problem is to step away for a minute of looking at specific equations. And let's just focus a little more on the concepts of our derivative and then the graphical concept of what the derivative represents as well. So in this example, we have two graphs, the graph of a function f of x, the graph of a function g of x. And what we want to do in this case, so we've defined p of x to equal f times g and q of x to equal f divided by g. So let's do a couple pieces here. Let's say we want to find p prime at 2. So since p of x is defined as a product, then p prime of x is going to be the product rule. So let's say we do derivative of the first times the second plus the first times derivative of the second. Now we're evaluating p prime at 2, so I'm going to be plugging 2 into each of my functions and their respective derivatives. And I just have a righto there, and then plug in 2. All right, so now we need to find each of these values. So let's take a look, let's move left to right. So we have f prime at 2. So what I'm asking in this case is at x equals 2, what is the slope of the tangent to the graph of f, right? What is the rate of change of f? So if I come over here to x equals 2, come up to the graph of f, I'm looking for the slope of the tangent. Now keep in mind that both of these graphs are made up of line segments. So for any line, the rate of change of that function is the slope of that line, right? So when I look at that line, I just need the slope of that line. I could pick any 2 points on that line segment. So if I run 2, I'm falling 2 as well. So I'm going to have a slope of, so I'm going to have a fall of 2 and a run of 2. So I'm going to have negative 2 over 2. I'm going to have a slope of negative 1. So then let's look at g at 2. So now I'm at x equals 2, and I just want the y value on the graph of f, and that turns out to be what? 1, 2, 3, that looks like 4 is the y value on the graph of g. All right, then I want f at 2. All right, so at x equals 2, what's the y value on the graph of f? So again, we were at that point. The y value is 1. And then now I want the rate of change of g at x equals 2. So I'm back up here at that point. What is the slope of that graph? And I'm going to pick 2 points on that graph. So I would rise 2 and run 1. And so the slope on the graph there is 2. So crunching all of this out, what do I get? Negative 4 plus 2, and that's going to give me negative 2 as the value of p prime at 2. So for the next part of the problem, let's say we want to find, let me scoot over here so I have a little bit more room. Let's say we want to find q prime at 2. So if I'm finding q prime at 2, right, so again we had defined q of x as f over g. So we had q of x as f of x over g of x. So q prime, I'm going to do a quotient rule. So I'm going to do bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. And again, I'm plugging x equals 2 into all of these quantities. So q prime at 2 Q prime at 2 is going to be, and I'm not giving myself enough room here. Let me scoot down a little bit more. So Q prime at 2, I'm going to have Q prime at 2, I'm going to have G at 2, and then F prime at 2 minus F at 2, G prime at 2, and all over G at 2 squared. Now I found all of those values already, didn't I? So G at 2 I know is 4 from up above, right? So I'm looking up here at what each of my values are that I had already calculated. So G at 2 was 4, and then we have F prime at 2 we found to be -1, and then F at 2 we found to be 1 up above, and then G prime at 2 we found to be 2, and then all divided by G at 2 squared, so that's 4 squared. So if I crunch all of that out, I'm going to get -4 minus 2 over 16, so that's -6 over 16, which both of those are divisible by 2, so I'm going to get -3/8, that is Q prime at 2. Let's take a look at another example, and just like our prior example, I want to focus more on kind of the bigger picture here instead of the mechanics of looking at specific equations. So in this word problem, I paused the video and put this problem on here so you didn't have to watch me write all of this out. So this problem says that the biomass B of t of a fish population is the total mass of the members of the population at time t. It is the product of the number of individuals, N of t, in the population and the average mass, M of t, of a fish at time t. So in the case of guppies, breeding occurs continually. And let's suppose that at t equals 4 weeks, the population is known to be 820 guppies, and it is growing at a rate of 50 guppies per week, while the average mass is 1.2 grams, and it is increasing at a rate of 0.14 grams per week. So the question here says, at what rate is the biomass increasing when t is 4? So just to highlight a couple things here, right? The question being asked is, at what rate is the biomass increasing? So the rate being the derivative. So we need to find the derivative of the biomass. And again, what is the biomass? Well, the biomass was defined as the biomass is the total mass of the members of the population. It is the product of the number of individuals, N of t, in the population, average mass, M of t. So we have the biomass as a function of time is the product of the number of individuals, our population, right, times the average mass. And we're wanting to find the rate of change of the biomass. So in this case, because biomass is defined as the product of N and M, we're going to use the product rule. So we'll have, let's say, derivative of the first times the second plus first times derivative of the second. So we're wanting to find the rate of the biomass at t equals 4. So we're looking for B prime at 4 weeks. So we're going to have the rate of change at 4, and then M at 4 plus N at 4, and then M prime at 4. So to finish this problem, right, we need to be able to find all of that information within the context of the problem here and the information that is presented to me. So first of all, what do we have here? So when I look up in my problem, I need to find N at 4, N prime at 4, and N at 4. So that's my population, right? The number of individuals, number of guppies. So I'm told that in the case of guppies, right, in the case of guppies, breeding occurs continually. Suppose that at t equals 4 weeks, the population is 820 guppies, and it's growing at a rate of 50 guppies per week. So the rate of 50 guppies per week, right, there's my M prime, and then we were told that the number at 4 weeks was 820. So those values I have down there. And then now I also need to find m at 4, right, the average mass, and the rate of change of average mass. So we're told here that the average mass is 1.2 grams, right, at 4 weeks, and it's increasing at a rate of 0.14 grams per week. So my mass at 4 weeks was 1.2 grams, and it is increasing at a rate of 0.14 grams per week. So now we'll go ahead and plug all of that information in here. So we have 50 guppies, and then the mass was 1.2. Sorry, this was n prime is 50, and then the mass is 1.2, and then the number of guppies was 820, and the rate of change of mass was 0.14. All right, so let me stop for just a second. I want to talk about units of measure here. All right, so we have guppies as our number. Right, so I'm going to write guppies up here, and then we have guppies per week. I'm going to get lazy and say guppies per week there. And then the m was the average mass, so we had the mass being 1.2 grams, and then it was increasing at a rate of 0.14 grams per week. So let's think of what our units are going to be in this problem. So the n prime at 4 was 50, and I'm going to say guppies per week, times the 1.2 grams. And then plus, we have 820, which was the number of guppies. And then we have 0.14, we had grams per week. So I'm going to think of this, right? This is like grams of guppies per week. And this is, well, this is guppies times grams per week, right? So this is grams of guppies per week. Grams of guppies per week. So that's going to be our rate of change of biomass, the units that we have there. So go ahead and take out a calculator and crunch that number. So I'm going to get the 50 times 1.2 and the 80 times 0.14. So I'm going to end up with 174.8 grams of guppies per week. All right, so let's take a look at one last example. And in this example, I just want to bring up the idea of multiple derivatives, right? So we've been talking about first derivative. We could have a second derivative as well, right? We could even have a third derivative. So for this example, let's say that we have y equals x cubed plus 2x times e to the x. We typically wouldn't see that parenthesis there, right, times e to the x. And what I want to do, let's find the first derivative, let's find the second derivative, and let's find the third derivative. So if I find the first derivative, y prime, right, I have a product rule here. So I have the derivative of the first. I'm going to write that out. Derivative of the first prime, right, times the second, and then plus the first times derivative of the second. Right, so in this case we have, what's this going to be, 3x squared plus 2 times e to the x, and then plus the first, and derivative of the second is e to the x. So here's our first derivative, y prime. All right, now when I go to find the second derivative, y double prime, what I could do is I could treat this as its own product, and I could do the product rule of this term, and then I can add, and I treat this as another product, and I could do the product rule of this term. That would all be very legal and legitimate. I personally want to avoid that if I can. It's not always avoidable, but in this particular example, it is avoidable, right? So I have an e to the x that's common between these two terms. So what I'm going to do first is factor the e to the x out. So I'm left with 3x squared plus 2 from the first factor, and I'm left with x cubed plus 2x from that second factor. So if I clean that up a little bit, so I have x cubed as my leading term. I have a 3x squared. I have a 2x and a 2. So all I've done is, because it was an opportunity, right? It was something that I could do. I avoided doing a product rule here and a product rule here, and I now have just simplified, and I'm only going to do one product rule as I find my second derivative. So now that I'm going to find my second derivative, right, I'm going to go ahead and use the product rule again. So I could do the derivative of the first times the second. Right? Or basically just repeat this process however many times we need to. Right? Oops, derivative of the first times the second, and then I have plus the first times the derivative of the second. X cubed, 3x squared plus 2x plus 2. I'm going to run out of digital paper. Ooh, I squeezed it in. All right, so there's my product rule, and then let's just go through each of these. Right? So I have derivative of e to the x is e to the x, and I get x cubed plus 3x squared plus 2x plus 2. And then plus, I have the e to the x, and then times this derivative. So the derivative of x cubed is 3x squared, and then we're going to get 6x plus 2 there. Now again, technically I'm done with the second derivative, but I'm going to go ahead and do some cleanup here. So there's an e to the x in common between the two of these terms, so let me factor that out. And again, what's going to happen here is I'm going to have, from the first factor, 3x squared plus 2x plus 2. And when I factor this out, what I'm left with is 3x squared plus 6x plus 2. And then I'll go ahead and combine like terms within that factor that we end up with. So let's see, I only have one x cubed term. I have 3x squared and 3x squared. That's 6x squared. 2x and 6x is 8x, and then 2 plus 2 is 4. So here would be my second derivative for that particular function. And I could continue. I could repeat this process, or I could find a third derivative by taking the derivative of the second derivative. And then I could find a fourth derivative if I wanted to. Right? So I could keep differentiating over and over again up to a point that we would be asked to do such a thing. Now, in applications, we talked about velocity. We talked about if an equation gives me height, the derivative is velocity. Something we'll talk about really soon is that the second derivative represents acceleration. So when I'm looking at an application where I have height or position as my function, right, so if y is height, or position function. And keep in mind, usually, we have units like feet or meters or, miles, something like that, right? Then y prime is velocity. And those units, right, would typically be, something like feet per second, miles per hour, stuff like that, right? And then y double prime would be acceleration. So it's the rate of change of the rate of change. So y double prime is acceleration. So in essence, I would have, let's say, like the derivative of this function, feet per second. So that would give me feet per second squared. And those are the units of acceleration. Or, I might have miles per hour squared, or meters per second squared, so on and so forth. So higher order derivatives, right, second derivatives, even third derivatives, will have some application for us very soon. And the reason I bring this up is for the past couple videos we have gotten a little sidetracked for good reason, but we've been focusing on skills. We've been focusing on derivative rules or shortcuts. And in the prior chapter, what we discussed was that a derivative was a measure of rate of change. And in word problems such as position or height, right, we saw what that application of a rate of change was. We also saw visually the derivative gives us the slope to the tangent. So we've kind of forgotten about those applications, those bigger picture concepts, and we've dwelled on the kind of the minutia of the shortcuts and the rules. We definitely want to do that. We definitely want to develop those skills, but we don't want to forget really what those applications are all about. We will continue to still focusing on some of these skills and shortcuts over the next video too. And when appropriate, we'll try to remind ourselves of the bigger picture, the application. And then in a couple more videos, one of the sections here is we will have a whole video where we'll discuss applications. So once we've discussed all the shortcut derivative rules, we'll come back and we'll say, hey, let's take the bigger picture look and look really at applications and why we're doing derivatives or rates of change. All right, I'll see you in the next video.